Okay, so this is what we were doing. So for lambda equal to 4, we found the eigenvector, which is half and 1. And next we take the second case, which is lambda equal to -2. So you have a minus lambda into x equal to 0, and lambda here is -2. Therefore, you have a plus lambda I, and that matrix a plus 2 lambda I, 2I is what I've written here. So you have the augmented matrix a plus 2I and augmented with 0. So again, you can use the row reduced echelon form to find the upper triangular matrix, and then you can write the equation. So here you can see that the second and third row is just zeros. So you have x1 plus x2 minus x3 equal to 0. And from here you can easily find the eigenvectors. So you'll have x1 equal to x3 minus x2, x2, x3, and then you can do the process which we have done in module 4 to find the eigenvectors which are associated with eigenvalue lambda equal to -2. So that is the process to find the eigen vectors. Okay, you need to find the eigenvalue first. Something interesting which I'll tell you, these are things which I've covered. So they just put on the slide for your reference. We are interested in solving the numericals. So all this I've explained to you, so I'm going to skip it. Yeah, so something important which I'll tell you is if you convert the matrix into its reduced echelon form or an upper triangular matrix like this, then you'll see that the eigenvalues are just on the main diagonals, right? So that's what is written here. The eigenvalues are on the main diagonal when A is triangular. So if this is an upper triangular matrix, because the main diagonal is having certain values, whereas the components below them, below this main diagonal, are 0. Therefore, the first pivot is 1 minus lambda, first non-zero value. The first non-zero value in the second row is 3 by 4 minus lambda. That's a pivot because the value below it is also 0. And then you have the third pivot, right? So the main diagonal in this case will just give you the eigenvalues. So that is something also which we can use. But the main idea here is to find the eigenvalue and then the eigenvectors. So let's look at another problem, and I'll just see if we have any newer problem which we can look at. Yeah, so there's a problem on trace. So let's see. Okay, so this is a problem which I solved from the prescribed textbook, which is Gilbert Strang. So the question is, you're able to see the PDF, everyone? Anyone, you are able to see the PDF?
Yes, sir.
Yes, sir.
Okay. Okay. So the question is, find the eigenvalues and eigenvectors of the matrix A, and A is 1, -1, 2, and 4. And you also need to verify that trace equals the sum of eigenvalues and the determinant equals their product. So let's look at the second part later. First, let's find the eigenvalues, right? So what do I do for eigenvalues? I have A and A minus lambda I. So I've written A here and then minus lambda into I. And first I find the characteristic polynomial A minus lambda I, and then I find its determinant. So the equation turns out to be lambda square minus 5 lambda plus 6. And the characteristic equation is nothing but characteristic polynomial equal to 0. So lambda square minus 5 lambda plus 6 equal to 0. And once I factorize it, I find the factors as 3 and 2. Right? So this is a simple procedure to find the eigenvalues. Now we'll concentrate on the second part. So what is the trace of a matrix, right? So let me go back to the slide for a second, and then I'll tell you what is trace. The sum of n eigenvalues equals the sum of n diagonal entries, and that is nothing but the trace of A, which is lambda 1 plus lambda 2 plus till lambda n, right? And more clarity on this is lambda 1 is nothing but A11. That means the first component of the first row and the first column. plus so on till a and n, which is the nth entry of the nth column and the nth row, right? So if you have A, B, C, D as this 2 cross 2 matrix, then its trace is nothing but A plus D, the main diagonal, and the determinant we all know is AD minus BC, right? So let's see how we can find the trace in the given problem. I'll go back to the PDF again. So the given matrix is 1, minus 1, 2, and 4, right? So to find the trace, I write 1, minus 1, 2, and 4, which is A, and the trace is nothing but directly the addition of all the elements on the main diagonal, which is 1 and 4. Therefore, the trace of A is just 5, right? Now, interestingly, what they've asked us in the question is verify that trace equals sum of the eigenvalues, and we found the eigenvalues as 3 and 2, and the trace is 5, and also 3 plus 2 is 5. So we have verified that trace is nothing but the sum of the eigenvalues, right? So there are two ways to find the trace. One is you just add up the main diagonal elements, or you just add up the eigenvalues. That will be the trace, right? The second question that they've asked is verify that the determinant equals their product, right? So we take a minus lambda I into x equal to 0, and then we first plug in lambda as 3 because the two lambdas are 3 and 2. So I first plug in the value of lambda equal to 3, and the matrix is minus 2, minus 1, 2, and 1. And I know that X will have a structure, a column matrix of n cross 1. N now is 2, so I'll have a 2 cross 1 matrix. So you have a 2 cross 1 matrix equal to 0, 0, right? So here I have minus 2x1 minus x2 equal to 0, and 2x1 plus x2 equal to 0. There are two unknowns, two equations. You can use the cross multiplier or the Kramer's equation to find the value. And x1 from all this will turn out to be 1 and minus 2, right? I do the same thing for the next part where lambda is equal to 2. So I find the equation will be minus 1, 1, 2, 2, x1, x2 equal to 0, 0. And therefore I find that the equation here is minus x1 plus x2 equal to 0, 2x1 plus 2x2 equal to 0, and I can solve this, and the eigenvectors turn out to be minus 1 and 1, right? So I have found the two eigenvectors. The first one is 1 minus 2, and the second one is minus 1, 1. The original matrix A is 1, minus 1, 2, 4, and the determinant of A is 4 plus 2, which is 6. And the product of the eigenvalues lambda 1 into lambda 2 is 3 into 2, which is also 6. So I've also verified the second, right? And I've also found the eigenvector. Right? So this is one of the problems from the prescribed book which I have solved. Okay? So there's one more problem which I have solved. You can go through that. I'll share the PDF. Okay. Uh, and there are many other problems. The process is the same. Okay. So the process will remain the same. You need to first find the eigenvalue, and from there you need to find the two eigenvalues. Okay. So there are many more examples which I've solved. You can go through the examples. I've also given you an example of how to find the trace, right, and how to verify if the matrix is triangular in nature, right? So, anyone has any questions on this? Anyone has any questions? Okay. Today's lecture we've done the eigenvalues and the eigenvectors, right? And then tomorrow's lecture we'll start with diagonalization, how to diagonalize a matrix, and then an important concept of singular value decomposition. Okay, so maybe tomorrow, if I finish, then we can discuss on the questions which are given in the model question paper. Okay, I've made solutions for those as well. If you are able to finish tomorrow, then we can discuss it day after. Otherwise, we'll continue with this day after, and the next week we'll look at the problems of the model question. So I'll be sharing this slide and the numericals. we can go through them. So any questions, anybody? Okay. There are no questions, then in that case, we'll end the lecture. Okay. So I'll see you tomorrow.